Welcome everyone to our meeting, our lab meeting this week. Actually, not a lab meeting. This is the replacement for our Monday meeting. One of the things I want to do today, a couple things. First, I hope you saw the announcement that just came out about a new course that has been released, and that course is called Cloud Security. All right. It is branded by the Cloud Security Alliance, and it actually does have a certification that maps to it. If you go under course resources, you can see the class listed under the security options. You can also see that for instructors, for institutions, excuse me, this can be put out as an independent curriculum, so you can do it as a self-study, or you can teach it as a class to your students, but there's no needed training for you as an instructor. So as long as you have the instructor role, you can actually create this class right now. It is designed to be about a 35-hour class, so it's not a super long class. So it could be something you could add into, let's say you've got a Security Plus class you're teaching or another class. So you would be able to do that. And if you want a little more detail, if you click on the English item right here, there's an overview and a fact about the class, and even a scope and sequence that will tell you, what's in here. So looking at cloud security, there's no official prerequisite. So it is designed to be a lower level security, but it allows you to take the CCSK, so cloud security cloud security credential. If you look at the course structure, there's 6 different modules. One is talking about what the cloud is, what is the infrastructure security for the cloud. So looking at how do we secure the cloud and its different components, how do we do managing risk, data security for cloud computing, so different storage models like different types of doing containers, doing storage and storage devices. I hadn't read the class, I hadn't looked at it, so I don't know exactly what they're doing with their storage models there. All the way down to security operations. So it's a good little addition. The beauty of it is it's free. If you are a Cisco Academy and you want to teach this, you can start teaching it tomorrow. What I did, and what I would suggest you do if you want to see what's in it, is if you have the instructor role at your academy, just create yourself a little test class, and you can go in here and you can look at what is available. So one of the things you do have to do is you have to kind of accept the terms and conditions. So it goes in here and talks about all those. So I won't bore you to death with that, but you do have to go through and do that and look at the different conditions, and then basically read through all these, and I'll do that later. But the class itself is 35 hours. And then at the end, you should be able to actually get a 20% off voucher for the exam. Okay, so pretty cool.
This looks like a good add-on to a Cloud Plus or a Security Plus.
Agreed. Yeah, I think it'd be really good to add on to either one of those as an additional thing the students could get. And really, even if they don't take the certification exam, it'd be a good thing to have to give them an opportunity to learn more about cloud security, because it is a big deal. So I just wanted to show that to you because I wanted you to see that it was available. And that's one of the advantages of being part of the Cisco Academy, is they do put out additional courses like this. Usually every year the portfolio has at least something added to it. In the past 2 years or year and a half, we've had this plus DevNet added. So they're constantly adding to the curriculum. They're also constantly updating it because we are on version 7, which is the one that maps to our current CCNA, that is the CCNA certification. Any questions before we start talking about path determination today? Because I want to talk about routing concepts, routers, and path determination.
Can I ask a question about the academy first? I wonder, right now we can access the CCNA 1 and 2 and probably 3. Now, how long can we access those things? Can we have
once our class ends, what you will need to do, Dr. Hugh, is create yourself your own class. So you'll go in, if your academy's up and running, you will have an I'm teaching tab. If you don't, then it means your academy may not be running yet. In fact, I'm gonna turn my video off. Y'all don't need to see my face. So if you don't have an I'm teaching, we may need to work with your main contact, or if you want to be the main contact at your school to get your academy fully up and running. But once you have that, you can create yourself. You'll basically go in to create a course, and you can create it inside of your academy, and you can just pick CCNA 1, Intro to Networks. That's the first course. And then you could create a course for yourself, version 7.02, give it a name. I would call it, like for you it'd be Dr. Hugh or Hugh test course. For me, it'd be ITN or intro dash KFC test. So that's my initials. So I would just make myself a test course so that you could go in and look at the materials inside of the course. So that's typically what we do. We just create ourselves a little test course that's available.
All right, that helps. That's great. Thank you.
And you can do it as soon as you're accredited for the course, like you're accredited for CCNA 1 now. So as soon as the one class that you're in for us is over, just create yourself a class. And then once you become accredited for the CCNA 2 class, then you will be able to do that. The other thing, I did send out an email today talking about what we have left to do for the course. And I'm pretty much caught up on grading. So grading's pretty much caught up, but many of you have moved along well in this course. But look over that email I sent out today talking about what needs to be completed to be able to finish the course before your next set of courses begins on the 30th of September. That is a good reminder that you will start CCNA 3 with Kirby Simerson on September 30th. And he will be your instructor for that course. And so we'll get all of you registered that want to be in that course. You don't have to do anything on your end. I will register those of you who have participated in this course and are looking to finish this course in the CCNA 3.
So you want to teach the 3?
I am not teaching 3. No, I am. I've actually taught my entire load for the spring,
Okay.
for the fall with this course and the ones I taught over the summer, because I taught overload in the summer. And so I'm going to back off. I've got to actually get, believe it or not, I've got to pass my DevNet by October 2nd, or my code expires. I have, by the way, if you have vouchers or discount codes, I have a discount code for my CCNA, or for my for my DevNet. And if I don't use it by October 2nd, I lose it. So that's one thing I've got to do. I'm also going to spend the rest of the fall renewing my CCNP. So I've got some things I've got to do on my end to get some studying done.
Okay, I have a good time with you.
Yeah, I enjoy it. I think you'll like Kirby. You've been watching his videos. Kirby is a very he's former naval guy. He's actually worked on nuclear engine. I was a nuclear engineer in the Navy.
Yeah, and he talks Navy too. Slow.
He talks slow. Yeah, he's real slow. I pick on.
It's one of those that you got to pinch yourself to keep up.
Yeah, it's funny. So what I want to do is I want to talk to you about path determination. So a router is a layer 3 device that does path determination. The other thing, let me ask you this: what kind of addresses do we work with at a router level?
IPs.
IP addresses, which are also logical addresses. So IP addressing, which are logical addresses, as opposed to physical addresses like MAC addresses. So now we're up at layer 3. At layer 3, everything is being done in a very software-based environment, okay? Because you've never held an IP address in your hand. Probably not anyway. So we're up at logical addressing. Routers, their main function is path determination. So each router is going to have a routing table. And in order to route something across, it looks at its routing table, and it's going to make a decision based upon its routing table alone, and then it will forward it. So if something comes in destined for a remote network, the router will look in its routing table, see if it has a route. In this case, you can see it has what's called a static route, this S route. We'll talk more about that in a second, to the 192.168.3.0 network.
Mm-hmm.
via 192.168.2.2. So it's saying in order to get to the 3 network, send it over to R2. Now, just because I know how to get there doesn't mean R2 is going to have the ability to get to the 3 network, because routers make their decisions based upon their routing table alone and then forward it and hope that the other router has the information it needs. We also cannot assume that just because router 1 has a route over to the 192.168.3.0 network, that there is a route back from R2 to the 192.168.1.0 network. And we'll talk about those rules of routing here in a minute. But in this case, it does have one. It goes down, there's a match for 3.0. It forwards it over to R2. R2 will then look in its routing table to see if it has the 3 network. And in this case, the 3 network is here, but it's directly connected off of an interface. So in other words, there's an IP address on fast Ethernet 00 on R2 that is on this network. And then it will forward it out the fast Ethernet 00. So each hop makes a routing path determination by taking that packet apart and looking at it and figuring out where it needs to be forwarded. The question becomes, how do you find in that table the best match? Well, the best match is the longest match. So you'll see if I was sending something to 192.168.3.10, the 3 network, the first 16 bits in all 3 of these particular route table entries match. But when we get over here to the 3.0 network, you'll see the longest match is the 3.0. And so that's what they mean by this. The longest path, or the best path, equals the longest prefix match. So if you're looking at all these different prefixes here, and you were trying to determine which one of these would be used to actually forward the packet, it would be the one that matches the most number of bits in the destination network. Okay.
So it's the whack that tells us which is the best path.
Correct. Longest match is the best path. IPv6, same thing. The longest address path match, most number of bits that match, is the route that gets used. So in this case, okay, this is 64 bits. So this is saying that 555 would have to be in this C000. Well, we don't have that. So our longest match here is the /48. So it matched 40 bits here, it matched 48 bits here. This does not match, okay, because it doesn't match 55. It's not subnet 5555. So the correct match is the /48.
Okay, so it's within network longest whack address.
Correct, exactly. It has to be within the network. Otherwise, you know, for instance, if this up here had a /28, but it was the 173 network, it's going to ignore it because that doesn't match. You know, the 173 doesn't match 172, so it wouldn't even match the first 3 bits, basically 3 or 4 bits.
Would it even include it because it was outside of the band?
It's in the route table, but it would be pretty much immediately discarded as not being a viable entry, because it would look, you know, if it was in the route table entries and it was route table entry number 1, it would look at it against it, but it would almost immediately say, well, that's not going to work because I've got a better match already.
Okay.
And we're going to talk about Cisco Express forwarding, process switching, and Ceph here in a minute on how routers actually do the lookup, because there's ways to make the routers do the lookup faster. So here we have a routing table, and if we look at this particular network here, you can see that on R1, how many connected routes would there be in the route table if all the interfaces were configured and they were up?
Direct connect or connected?
Connected, directly connected. Connected is only directly connected network. So if it says connected, got the C, it has to be a directly connected network on the interface.
5, pretty
2.
much every IP address, right?
You're real close. You're real close with 5, but I'm gonna tell you, first off, there's going to be 1 here for IPv4, the 10.0.1.0 network, and there's also going to be 1 here for the 1 subnet of 2001 DB8 ACAT. So it's a little bit of a trick question. So there's 1 IPv4, 1 IPv6 here. There's one IPv4, one IPv6 here, one IPv4, one IPv6 here. So it would really be 6.
So
I
2
s-
per
I saw that.
connection, assuming dual band.
If they're dual homed, running both protocols. Correct. Now, over here, all of these networks are networks that we are not connected to directly on R1. If R1 was configured to be able to have reachability to these other networks, it would have a remote network in its table to these two, the IPv4 and IPv6, these two and these two, and it would have what is called a default route that says anything you don't know how to get to, send it to R2 and let it send it up to the ISP. All right, but we typically have directly connected networks and we have remote networks. Those are our 2 primary types of networks. So our remote networks can be static or dynamic. In this course, we really only deal with making static routes. So we're not going to be dealing with dynamic routing protocols in CCNA 2. We will be doing it in CCNA 3. You're going to learn about OSPF single area. And then there's what is called a default route, which is a route of quad 0/0 or ::/0, which basically says if it matches no other prefix, send it here. It's also sometimes called a gateway of last resort. So if that's set, it will send it over to wherever that is, and it will try to send it. Let me ask you this. Here's a really good question. What happens if something comes in, a packet comes into a network that a router has no route for in the route table? What will the router do with it?
It'll send it to whatever the default address is.
If there's a default route, you are correct. It will try to send it using the default route. But what if there's no default route?
It'll drop the path.
It drops it. It drops it and sends back an ICMP destination unreachable. So if there's no route in the routing table and there's no default route, it gets dropped. It will not route it. Okay. The other thing we will learn is that typically with almost all the routing protocols and the routing tricks that we use, typically a router will never route something to a network that it doesn't have a path to. BGP gets a little weird there, but for the most part, it's going to have some type of directly connected path to be able to get it there. It's going to have reachability in some way. So here we can see our forwarding process. So destination IP address comes in, the router will look in the routing table, find the longest prefix. If no prefix is there and there's no default route, it goes in the bit bucket. If there is a prefix, it will use that longest prefix to try to forward it to the destination. If there is no prefix, but there is a default route, it will then try to use the default route as the method to route. So basically, we have the ability to forward to directly connected networks to the next hop router, or dropping it if there's no other route. So here we see it. PC1 wants to send to PC2. So it's going to forward because it's got its default gateway. One of the first things that happens is this. PC1 will take its IP address, will AND it to its configured subnet mask to find out what network PC1 is on. It will then take the destination of 192.168.4.10 and AND it to PC1's mask and find out that PC1 and PC2 are not on the same network. If they were on the same network, PC1 would just put it into a frame and send it over, but they're not. So PC1 sends it to R1. R1 will look at it and say the destination network is 4.10. And so it will look into its routing table and hopefully find that it has a path to 4.10 or the 4.0 network over on R2. So it's going to forward it over to R2. The thing about it is R1 has to take this completely apart to look at it up to layer 3 and then repackage it with new layer 2 information to forward it to R2. R2 grabs it, does a lookup in its table, determines that R3 is the next hop, and it is available on the serial link, which means we're going to have to completely change even the type of layer 2 information, because it's no longer Ethernet. This may be HDLC or PPP, just depending on what you're running here. And then finally, R3 gets it, sees that that network is available via its own G000 interface, and will forward it out to PC2. Now think about this, folks. We gripe about the internet being slow, and this has to happen for every single packet we send somewhere. So it's really pretty amazing. I mean, absolutely amazing that it takes place.
So I remember in a packet trace that I don't know which one. They say on left hand side, in this network .1, like a, and on the right hand side, they're pretty much on the same network.
Right.
The two computers on the same network, but they pass through the routers and everything there. Now, when these, actually that time I was confused. I'm not sure I remember correctly, right?
Right.
So when this PC1 send a package to PC2, they're supposed to directly send to it, right? Because that's on the same network.
PC1 could not send it directly to PC2 in this network because PC1 is on the 192.168.1.0 network. PC2 is on the 192.168.4.0 network.
So you basically cannot have PC1 and PC2 on the same network in this case, right?
No, you cannot, because they've got different IP addresses. They're on totally different. This is the .1 network. This is the .4 network. So they're on two completely different set of IP addresses.
So
two different networks.
So how about this situation? Let's say we have a room in ASU. We use 192.168.1 network /24.
Okay.
Now we also have a room in Stanley College that use 192.168.1 network, same network.
Yep.
But pass through the bunch of routers there.
Now, all right, I can explain this to you. All right, so what you're looking at and what you are dealing with is, remember back in our last class, we talked about a set of addresses called RFC 1918 addresses. These are the private IP addresses, remember? Oops, we'll just leave it at private IP addresses. And remember the ranges. One of the set of ranges was 192.168.0.0 to 192.168.255.255. And what I told you was that these can never, ever, ever be routed across the internet. So what's happening is this, Dr. Hugh.
Okay.
Say this is Stanley's network here, and this is my network, and we're using 192.168.1.0/24 inside of here. This, though, connects to a router, and this router connects to the internet. Okay, so here's the internet. Now over here is your campus network, ASU's network, okay? And inside of here, you've got a switch and you've got a network, and in this network, you are using 192.168.1.0/24. What we have not discussed with you yet is we have not discussed a concept called NAT, or Network Address Translation. So what is really happening is this: although you're using 192.168.1.0 inside, that cannot go out on the internet. It cannot be used by the internet. So your campus network out here at the edge is converting this to some kind of public address, 209, 204, 211. I'm making this completely up, but it could be some 200, okay? On my side over here, my network is doing the same thing. I'm using some, let's say 138.15.10.10. So we are natting, or doing network address translation between these private addresses and our public addresses.
Okay.
So even though we've got the same address on the inside, they're never seeing each other.
Mhm.
They
So
cannot see.
here's a
Go ahead, Dr. Hugh. I dropped my pen. Hold on a second, y'all. I got to get under my desk to get my pen.
The
okay.
other thing is they're provided by your internet service provider
Correct.
because you're a Class C network, no matter what campus you're at.
Mhm.
So the address block that you're going to have within your network will always be in the 192 range.
Mhm.
Well, no, not necessarily. Not necessarily, because it really inside of here, I'll give you a good example, Steve. We don't use this. We use 10.0.0.0/8 because that's one of the other addresses.
Right.
So
Right.
everything inside of our network is a 10.
Okay,
So-
but it's either that or 192 because
Right. It's
you're
either
not going to go
10.0.0.0,
outside the.
it's either 10.0.0.0/8. It's the 192, which is the C. This is the A. And then the B address range is 172.16.0.0 to 172.31.255.255. So these three sets of private IP addresses will always be what are used on the inside. And then on the outside, you NAT to whatever your ISP gives you.
So here's another question, because I see quite a bit there when we draw this similar graph there. One computer to switch to router to
Yep.
another router to there. Now I see so often there between the routers you use IP address that is 192.168. So basically, in reality, we don't use that type of address, right?
Not to go outside your network.
Internally, we do. But outside, we don't. So
schedule.
for instance, let's imagine right here. Let's imagine what
Okay.
really happens. I know I'm not drawing it. There's another router right here.
Mhm.
And let's imagine this router is owned by AT&T.
Mhm.
Okay. The connection, let me get me a different color here. The connection between my campus and AT&T right here
Mhm.
has to use
Yes.
public IP addresses.
Okay.
All right. Same
Okay.
thing over here. Over here, let's say this is Sprint or whoever. So this is Sprint, Verizon, whoever. Okay.
Mhm.
This has to use public IP addresses.
Mhm.
Okay. Well, I say it has to. For simplicity's sake, let's say it's going to. It doesn't have to. It could use private, and then they NAT somewhere inside of them. But typically, they're on the outside edges. They're public because they have to allow the access to certain devices and things on the inside.
Mhm.
That's why I use these numbers, and they are in there. Let me change that. They are inside addresses because they are considered what I say private addresses. They're never going to go through this router. In fact, this router right here at AT&T is blocking all of the known 1918 addresses. It won't allow any of those to come in it
Mhm.
because they're not routable addresses on the internet.
Mhm.
But
Yes.
they are intranet addresses within your network.
Correct. They are fully routable within your network. They just cannot be routed across the internet, across the public internet. That's why they're called private IP addresses.
Mhm.
If we did not have this, we would all be running IPv6 already on everything we have, because the only way that we don't have IPv6 on everything is because we're NATing everything.
Mhm.
Because you got to think,
Yeah.
our little podunk network here in North Carolina, I mean, we have 400 to 500 clients on our small network. So imagine, like a large university or a large government entity, how many different hosts they have. And there were only roughly 4 billion IPv4 addresses. So there were very few IPv4 addresses really even out there.
I don't even think there's any more for sale.
I understand this part. I'm confused because this picture on your screen there is that between routers R1, R2, right?
Okay. Well, and here's what I want you to understand.
Right.
This is for teaching purposes only.
Okay, that's
it.
okay.
That's the only they're showing this and using the private addresses for teaching purposes only.
Okay, all right.
Yeah. Typically in the real world, the connection, let's say the R2 was an ISP, R1 was your university, R3 was our college. These addresses between R1 and R2 and R2 and R3 would be public addresses.
Okay, that makes sense. Okay.
Yeah, so that's what they're doing here. They're just showing you what is going on for, you know, a test network. That's exactly right. Okay. Now let's look at the methods that can be used in order for a router to forward packets. So you got to think about every packet that comes through. By the way, you can watch this if you want to. It goes through it in a item by item thing, rebuilding the frame and everything. But every single time it goes through a router, it has to look at it. Now that's a lot of work and would be a great deal of work if we use the old method, which is called process switching. Process switching on a router, by the way, there's a data plane through which data flows and a control plane through which lookups take place for routing protocols or for routing at all. If we use process switching, every packet that comes in has to go up to the CPU, be enacted on by the CPU, comes in an ingress interface, gets a lookup, and goes out an egress interface. The analogy used for this is imagine doing longhand math all the time, even if the problem's exactly the same. So if every one of these packets is destined for the same network, we're still going to do the long lookup process before we send it out the egress interface. This is highly inefficient, highly inefficient. So another method that came around was called fast switching. And that's where if a packet needed to have a lookup, you would do a lookup. And then for every other packet destined to the same destination, you would have a fast forward cache. And so you would not have to go into the control plane before sending it to the egress interface. The analogy for that is you do the math longhand once and then save the answer for any identical problems later. And the one that's actually in use by all Cisco routers today is called Cisco Express Forwarding. And what this does is this: as soon as you start putting IP addresses into a router's routing table, it performs a lookup and builds what's called a forwarding information base, a FIB table, and an adjacency table. And it then uses that to send, if anything comes in, it's already done the lookup and it knows what egress interface it needs to go out. The example given is this solves all the problems and keeps it in a spreadsheet. And instead of having to go and try to solve the math problem, you just look in the spreadsheet and find the answer and send it.
So after all, you have like about, for example, the router have 24 ports. Now that two, okay, probably that the other target router have more than one, right? So then you multiply 24 by
Right.
24.
Well, remember,
That's,
most time routers don't have 24 ports. Most time that's a switch. Routers typically only have, 8 to 10 ports.
oh, okay.
But now there are switches that route. So even the switches, though, you think about when we go routing between them, we're only routing between VLANs. So even though we may have a switch with 24 ports, we may only have 3 or 4 VLANs we're routing between. So we don't have, all of those. And you know which ones they're associated with, so you can build that FIB table. So these 3 methods, I would know about them and know how they work. Cisco Express Forwarding is the one that we use today. I'm just going to blow through this. This is basic router configuration, so it gives you a review. So your host name, enable secret, put in your console password, your V2I line password, setting up SSH, service password encryption. This, by the way,
cheat sheet.
Yeah, this was if you just copy this onto a page, this is a massively good cheat sheet. Okay, because this is everything you need to do a basic router config. So that's a good hint for you that you could keep up with right here. Verification commands, we talked about show IP brief, show running config. What I want to do now, we're running out of time a little bit, but I want to show you something. I want to go in here and do some hands-on examples because I always believe that that's the best way to teach you. And that is this: we've got a router, and here's our topology. So we've got a router R1 connected to R2. We got gig 000 and gig 001. And I'm going to keep it fairly simple here. The first thing I want to do is show you that on IPnt brief, I have the most trouble with that. Show IPnt brief, you will notice there are no IP addresses at all on any interface, even though they're up, they are actually up. So let's do a show IP route. You'll notice there's nothing in the route table right now, nothing. Okay, so I'm going to debug IP packet, which by the way, you need to be very careful with debugging. It's a dangerous little rascal. I'm just doing it to show you some examples here, but I'm going to go to interface G. I think 01 is my internal. Yep. So I'm going to go ahead and use my own IP addresses because y'all know I like that. Going to global config T, interface G001, and I'm going to use the IP address of 192.168.12.1, 255.255.255.0. And I'm going to go now do show IP route and show you again. Notice the second I put that IP address on there, what happened? Now we have a route.
Direct connect.
Yep, we got a directly connected route. By the way, if you ever need to know, you can just look at your little cheat sheet up here and it tells you how you learned about it. This is directly connected. So in other words, I am connected to the 192.168.12 network on gig 001. And then because this is something they show you in the curriculum, we talked about it in CCNA 1, but you get this local route because it's iOS version 15 or higher. And that tells you what the actual IP address is on the interface. Okay. So if I do a shut, watch what happens. My route goes away. In other words, I no longer have reachability to that network. So it takes it out of the route table immediately. Do a no shut. Goes, but it takes a second because it's got to come up. So until that interface came up, okay, now it's up. You notice I looked at it twice and it's not in the route table. When the interface comes up, now it's back in the route table.
And you can't tell from a ping whether it's up or administratively down, can you?
You cannot. No, you cannot. No. So now I'm gonna go to the other interface, int G000, which by the way, a lot of times you'll notice, just to give you a little hint, a lot of times they use 001 as the internal interface, the inside interface, and 000 is the outside interface. I like to do that if I'm designing labs just because it makes it a little bit easier. But let's do IP add. I'm gonna do 172.16.0.1, 255.255.0.0. Okay. Now we'll do a do show IP route. And notice now we've got two directly connected routes. We got one to the 172.16 and one to the 192.168. Go over to R2. Let's see, since they're connected inside here, I'll put R2 on the same network as R1 over there. So do this and config T. Let's do a do show IP route. Nothing there. Int G001. IP add. I'm actually going to put them on a different network. 192.168.13.1.
Now, that gateway of last resort is not set. It's just telling me that there's no default route.
Correct. That is exactly right. If there's a default route, it'll have a star beside it. It'll have a star that tells you. And then let's do our outside, and this will be IP add 172.16.0.2. So now if I do a do show IP route, I've got a route to the 16 network, 172.16, and a route to the 192.168.13. In fact, from here, I should be able to do a do ping 172.16.0.1. It works. So I can ping from R1 or R2 to R1. But I cannot ping, what's this? If I try to ping to 192.168.12.1, it fails. Why?
Don't have a 12 network.
That's exactly right. You look in this route table. If I do a lookup to the 12.0 network, well, you know that's not going to match. None of these match because it's not going to match. 192.168.12.13 doesn't match. So I have no route to it. So I throw it in the bit bucket. Now, so let's make a route. Let's do IP route 192.168.12.0. This is a static route, by the way. This is the next chapter, but we're still going to do it. 255, 255, 255.0. And I'm going to say that it's going to the next hop address, which is 172.16.01. Okay. Now if I do show IP route, I now have a static route to the 12 network. So let's do our ping again. Okay. And it worked, which confuses me. Let me do something real quick. Let me find this FA01. Now we'll try it. So R2. Okay, let's do this. Let's drop out of here. Control Z. Let's do a trace route. 192.168.12.1. So it goes over to, should go over to 172.16.01. Yep, there it is. And then back. So let's do a show IP route. Oops, that wasn't what I wanted. Sorry, y'all. The reason I'm confused is I hadn't done a route back to no, that works. That works. That works perfectly. That's right. Because what it did is I now have a route to the 12.0 network and it goes over to 1. And let me ping it. It goes straight over to 1, ping, not pig, ping 192.168.12.1. It goes over no problem. Now watch this. So if I go to R1, you see all the routing going over here. That's why you got to watch out for debug. Undebug all. All right. But if I try to ping 192.168.13.1, you'll notice it's going to fail. So I've got connectivity from here over to R1, but I don't have connectivity from R1 into the 13 network. Because if I do a show IP route, you will see there's no route to the 13 network. So let's do a static route here. So do an IP route to the 192.168.13.0 network, 255.255.0, and it would be next hop of 172.16.02. Now we'll do a Control Z, up a couple here, and we should be able to ping, no problem. So now we have full reachability because we can route both ways. But you'll notice it only goes in the route table if show IP route. If we have a route to the destination, either a connected route or some type of remote route. In this case, a static remote route.
So we have to do it static manually. We won't be able to have a way to automatically figure out. Say
actually, yeah, you will, not in this course, not CCNA 2, but in CCNA 3, you will. So in other words, in CCNA 3, here's what you're going to learn how to do. Okay. I got to remember.
Okay, a wild card then to the short path.
Yep, and this should be all networks. Then I'll go back over here and do int, wait a minute, do router OSPF on network. And we should be able to go over here. So the that show IP route. Not learning it yet. I may have done that. It may be quad zero. Let me do the actual network statement. 192.168.13.0. There it goes. There we go. See, now we got our OSPF route. So
Right.
this is dynamic routing protocol. So in other words, R1 learned about the 13 network from R2 when R2 told about it with OSPF. You're going to learn how to do that. This course, though, CCNA 2, we're only doing static routes.
Okay.
Okay. So as we look here, as we continue on, I want to, again, let you look at the routing table. And as we see here, the routing table has connected routes and then a local route, which tells you what the actual IP address is. It could have remote routes. In this case, there's 2 OSPF routes on R1. On R2, you can see the same thing. There's 2 connected OSPF routes. There's also on this one a gateway of last resort. See that S star? R1 also has it, but you'll notice this is a special OE2. You're going to learn this is how OSPF can advertise a default route. So actually what has happened is R2 has the default route on it and is advertising that route via OSPF to R1. And so R1 says, anything I don't know how to go to, send it over to R2, which makes sense because R2 is who is connected to the ISP. So we've got a routing table full of different types of routes. You'll notice again, the star, important thing here is that's your candidate default route. And here's some principles I want to leave you with to think about, and that is this. Every router makes its decision based on its own routing table, period. Not its neighbors, nothing else, just what's in that routing table. If that table doesn't have a route to it and there's no default route, it will be discarded. If there is a default route, it will send it to that wherever the default route points to and hope the person upstream can take care of it. Number 2, the information in the routing table of one router does not match another router per se. Just because they're 2 routers in the same inner network, they're not all going to have the same routing table. And just because you've got a path to one destination doesn't mean there's a path back from that destination. This gets people in a lot of trouble out in the real world.
So maybe that let's say you send to the same place that go to a different frame, go to different paths, right?
Correct.
Mm.
But not only that, it means like this is really what they're talking about. Imagine a network. Imagine this network. Imagine that we've got a router, okay, connected to a router, connected to a router. Over here, we've got 192.168.12.0/24. 24, that's a 4, y'all. 4. This is .1, .10. This is 10.0.0.0/30. This is .1, .2. This over here is 10.0.0.4/30. This is .5 and .6. And then way over here is the 192.168.13.0/24 network. .1.10. I could go on R1 here. There's R1, R2, R3. I could go on R1 and put a static route of IP route 192.168.13.0, 255, 255, 255.0, and say my next hop is 10.0.0.2. So this would put a static route on R1 that said anything that is destined for the 13 network, send it over to R2. On R2, I may put a route that is IP route 192.168.13.0, 255, 255, 255.0. That's 5, y'all, sorry. And I put 10.0.0.6. So it says when that packet, if PC A sends something to PC B, it would come in. R1 would look it up and say, oh, that's destined for the 13 network. Send that over to R2. R2 would get here and say, oh, that's destined for the 13 network. Send that over to R3. R3 would go, oh, that's destined for the 13 network. I'm directly connected to it. Send that out here. But then B sends back a reply. Okay. R3 looks in its route table and says, oh, the reply is destined for the 12 network. I don't have an entry in my route table for the 12 network. It will then drop it and send to B a destination unreachable. So in this case, you can see there's a red path. There's a path from A over to B, but there is no path from B back to A. So just because there's a path one way doesn't guarantee there's a path back the other way. Now we could fix this by going to B, or going to R3 here and doing a route to 192.168.12.0, 255, 255, 255.0, and then do 10.0.0.5. So it says send it over here. Then we'd have to put a route on R2, same route, but pointing here to go here. And then we wouldn't have to put anything on R1 because R1 is directly connected to the 12 network. So that illustrates the idea that just because you've got a route one way doesn't guarantee you're going to have a route back.
That makes sense, yeah.
Okay. So again, routing table entries, we always learn what the source of the route table entry is. That's the first item. The second item is the network. The third item here is what is called the administrative distance. And that is a weird little beast, but it is a Cisco proprietary measure of the reliability of a route. Lowest you can get is directly connected, which is basically a 0. Static is a 1. And then you've got 110 as OSPF, you've got EIGRP at 90. But basically it says if you've got multiple routing, multiple ways to get to a destination, so multiple sources for the route table to a destination, then the one that will be picked will be the one with the lowest administrative distance. I compare it, what I tell folks, it's like how you're trying to figure out the best path or the best way to get somewhere. It's not the best path, it's the best source to get to a destination. So if I had this and I also had a static route to the 10.0.40 network, the static route is what would get put into the routing table, not this, because the static route would have an administrative distance of 1. The next item is your metric. Okay, so it's how the best path within a routing protocol. And then you've got how to get there, how long it's been in the route table, and the outgoing interface. So let's look down
I can
here.
remember when we were doing streaming videos. And if the administrative cost was more than 100, it was considered unreliable.
Trying to think of what that would be. I don't remember.
That was with the voice.
Yeah, that is setting a quality of service marker, which is a little bit different. It's
Okay.
a little bit different. That's a quality of service marker. So here's how we create a static route, IP route, the destination network, the mask, next hop IP address. All right, or you can do an outgoing interface, and we've got an entire section that we're going to do static routing, so I'm not going to spend a lot of time on that. Here's dynamic routing, but I do want to get down here and look at, talk about default routes. I want to talk about administrative distance. So imagine you've got multiple routes from different sources to the same network. So if you had a route to the network and for 3 different sources, one was a static route, one was an EIGRP route, and let's just say it's an internal EIGRP, and one was an OSPF route. The static route is what would get placed in the routing table because it has the best administrative distance. It is considered the most trustworthy source for routing table information. And that's how you can really describe administrative distance. It's the reliability of a source of routing information, the trustworthiness. The metric that you see listed second here, this metric is how good that is within a routing protocol. So if you were able to get to a route with 3 or 4 different OSPF routes, the one with the best metric would be the one that goes into the routing table. But if you had multiple sources of routing, then the one with the lowest AD goes in the routing table. That's the difference between a metric and an administrative distance. All right. I'll leave you with my little kind of funny thing that I do for AD. Okay. So we need to eat lunch. All right. Everybody likes lunch, right? So the first thing we're going to do is we're going to determine what kind of lunch we want to eat. What do we consider the best lunch? Do we want Mexican? Okay. Do we want just American cuisine, just a regular American cuisine? Do we want, some kind of Thai? All right. So we're going to make a decision of what type of lunch we want. And then the metric is going to be which one of these restaurants is the best. And so we may pick that based on price, food quality, service. Okay. So we use metrics to determine the best of the type of restaurant we're going to eat at. Administrative distance is those different types. Looking at it from a routing table standpoint, if you had a static route to the 10.0.0.0/8 network, you had an OSPF route to that same network, and you had a EIGRP route to the 10.0.0.0/8. You've got to determine which one of these goes on the route table. So you're going to look at the AD and you're going to say, AD for static is 1, for OSPF is 110, for the IGRP is 90. This is going in the route table. And it makes sense because guess what? If you take the time to statically put a route into the route table, that's probably the best route. Or it's at the very least, it's the route you want the traffic to travel.
So that is OSPF 110, that means this pass through more than one hop, pretty much, right?
This has nothing to do with hop because this is administrative distance, not metric.
Oh, okay.
Metric is a totally different thing. Metric is OSPF, by the way, for metric uses a thing called cost, and it's based upon the speed of the link, with faster links having a lower cost. So you'll find out about that as we move forward. But no, this AD has nothing to do with number of hops. Here's the funny thing, and I'm gonna let you in on a little dirty secret. AD is a Cisco proprietary concept. And so this is why EIGRP, which is a Cisco proprietary protocol, has a better AD than the open protocol OSPF. Cisco believes EIGRP is more trustworthy than OSPF. Many people would argue that's not true. Many people would argue that OSPF is more reliable or more trustworthy than EIGRP. And that's a debate that we could have for days, but.
So I wonder how do they, in this case, how do they like choose different port? That means different port, right? Pretty much.
Different ports?
Because the writing is said static, you go to
right. Static
metric.
OSPF.
Mm-hmm.
How does who choose?
Were they like for them a same package? Were they go to same port or different port if they choose different method, like the first one AS or OSPF? Yeah, I'm a little bit confused here.
Yeah, it doesn't deal with port. What it deals with is let me do this. Okay, let's go back here just a second. All right, so let's imagine. I'll show you a good example here. Let's imagine this. We got a router, okay. So let's do a very simple protocol. We're going to use the protocol called RIP, which we don't really study anymore. But RIP is the routing information protocol, and it's a pretty dumb protocol, okay? So we're going to go out here. First off, here's our two networks, here and here. All right. So let's imagine this. We've got a serial link here that is 768K. Okay, that's kilobits per second. That is very slow. Let's imagine that this link here is a 10 gigabit link. This is 10 gigabit. And this is 10 gigabit.
All right.
Okay. RIP has a metric that is called hop count. Okay. So the way RIP determines the best route to any destination is the least number of routers it goes through. So let me put some, this is R1, this is R2, R3, and R4. Okay. So RIP would say the best path to network V, so net V, the best path to V is R1 to R2. Because it goes through, if I'm going from network right here, so if I'm going from network Z to V, the best path is to go from R1 to R2 because it goes through exactly 2 hops.
Right.
Now, if it goes this way, it's 1, 2, 3 hops. But we know real world, this is a much faster route, correct?
Right, right.
99.9% of the time, three 10 gig links are going to be the 768K link every time. OSPF uses a metric that is called cost. It's based upon a speed, okay? OSPF would say the best path from Z to V is actually R1 to R3 to R4 to R2, okay?
Right.
So it would say the best path across the top. So the metric was used to determine the best path within the routing table, or excuse me, within the routing protocol itself. Now, R1 has to put a route in its routing table, correct?
Right.
It has one from RIP, it has one from OSPF to the same V network. Well, just so happens the AD for RIP is 120. The AD for OSPF is 110. So in R1's routing table, the OSPF route will be placed in R1's routing table. Now,
So basically at R1, if you choose different paths, you will go to different port.
correct. Yeah, you go through, you look at the different paths and the ports and determine the best within a particular routing protocol using metric. And then when you've got a route to the same network between multiple routing sources, you use administrative distance.
Okay, yeah.
Now, if I went into R1 and for some crazy reason, put a static route that said IP route to network V is by going to R2, that route would have an AD of 1. That route would take precedent and it would go in the routing table, even though it would be a dumb route.
Mm-hmm.
But at that point, it's going to come across here. And that would be crazy. But that's how I've got 3 routing sources: static, OSPF. See, this is a static source. So static, OSPF, and RIP. You look at the AD, well, the static route's going in the table because it's the one with the lowest AD. Does that make sense?
Yes, yes.
Okay, excellent.
Mhm.
All righty. Everybody, that's all I've got for today. We will come back on Thursday and we will get into our entire chapter on static routing and do some static routes and play around in our route tables and go from there. So thank you very much for being here. Let me stop the recording.